Well, good afternoon. It's 2:35. Sorry, 5 minutes late getting started for differential equations, but we wound up with having a projector removed from the ceiling in one of the classrooms. I went by to check on that and got to talking with the instructor about it, so it took longer than I intended. But anyway, let's get started now. I'll wait. No other student is in the room right now, so I'll wait and make any announcements after, if and when any student shows up. So, let me get on the right page here for my class. All right, here we go. All right, 238, got it. Okay. Where I have that we left off last time was on the top of page 133. This is Chapter 4, Higher Order Differential Equations. 4.2 is talking about reduction in order. Okay? Now, we were working on this problem. It's really a sort of an involved process here. Here was the problem. I'll try to rehash it as quickly as possible. Let me get my pen set up. Okay. You got a second order differential equation, y double prime plus p of xy prime, y prime, plus q of xy is equal to 0. Okay? Now, the form of that looks a lot like our linear equation did in a first order linear equation, except you don't have a q of x. A q of x or something like that is on the other side of the equal sign. But the form is looking like that the leading highest derivative has a coefficient of 1, and the next highest derivative has a coefficient they're calling p of x. Okay, now this doesn't necessarily have anything to do with the p of x we had in the other, but they're using the same terminology. But now we got the equation itself, the function itself, y, has a coefficient function of q of x, but now it's equal to 0 on the right. Now, we took it through and made the substitution. Y is equal to u of x times y1. Okay. Here's the sort of artificial thing here. Suppose we know that y1 of x not equal 0 is a known solution. So y1 of x is a known solution for this differential equation. Don't tell us how we know that. We just know that it is. Okay? Now, we're trying to find the second one, okay? And what we're going to do is define the second one, y. Why they don't call it y2, I'm not sure, okay? But y is equal to some u of x times y1 of x, the known solution we have, okay? And then we carried that through, did the first derivative, the second derivative, the product rules, all those kinds of things, and we came up with the fact that stuck in the middle was a term that looked like this, so we wound up with an expression that was, and I'll rewrite it, this is what we had left over then, y1 times u double prime plus 2y1 plus y1, 2y1 prime plus y1, and that p looks also like an r. My pen drug a little bit, so let me start over with that. y1 times u prime, and that's equal to 0. Okay, we got that far, and we notice there is no u. There's u prime and u double prime, but no u. So therefore, let's introduce another form, another function. Let w equal u prime of x. So w is also a function of x. W of x is equal to u prime. Okay? Now, let's plug that in, and what do we get? If w is equal to u prime, w prime is equal to u double prime. Okay? So now we have a y1 w prime plus 2y1 prime plus py1 times w is equal to 0. Okay? Now, they make the contention here. Okay, make sure I've got everything the way they do. Yeah. That this is both linear and separable. Certainly linear in the fact that you have some coefficient of x, only we're calling it y1 of x now, for the w prime, and a coefficient of x, same one we had up here, p of x times y1 of x times w, so that's just some coefficient of x, function of x. And then on the other side, oh, I'm sorry, this is all a function of x, okay? 2y prime of x plus p y1 of x, that's also a function of x, and that's equal to 0, okay? So that's a linear function. Now what they're suggesting here is this is also separable, okay? Now, I'm sorry. All right. Man, here's how my impression of how they're separating these. It's y1 times dw dx, that's the only variable here, dx, okay, plus, and what I'm going to do is write this is equal to a minus 2y1 prime plus p y1, all a function of x, okay, times w. Okay, I brought the minus sign up front. So what we're going to do here is write this in differential form, moving our dx over here, okay, and divide by w here. Oh, and also divide by y1 here, okay, and divide by w here. So what we have now is dw over w, there we've separated the w's on the left hand side, is equal to a minus, I don't know if this will be, okay, now that y1 I divided by looks a lot like a y prime. Let me get that one subscripted where it belongs. There. Subscripted where it belongs. There. It's not, this is aggravating me no end. Okay. y1. Okay, got it. Now, so your dw over w, which we know how to integrate that, is equal to minus 2y1 prime plus p, let's go on and write the y1 here, over y1 times dx. Okay? These are all functions of x. There's an x. This is all functions of w. Okay? So what we have here is log w. That is the antiderivative of 1 over w, dw. Now, I was starting to do it, but I hesitated, but I'm going to, let me go on and do this. Let's rewrite what this is. This is minus 2y1 over y1 prime over y1 plus p, because the y1's cancel out here. Let me put this as a minus p. Yeah, let's go on and make that a minus p. I want to make sure the book did. It seemed like it should have. Dx. Okay, we just divided out the minus y1 there. Now, and actually what they do is do a dx with this one and a dx with that one. Okay, so I'm just going to squeeze a dx in there. Probably going to remove my parentheses. Okay, now we'll integrate both sides. We'll integrate them separately. We already integrated this one. This becomes a minus 2y1 when you integrate that. Okay, no, 2 log of y1, sorry. Can't get that to erase. There it goes. Okay, 2 times the log of y1, and this would then just be minus the integral of p of x dx, which we've seen before. Okay, so let's move this back to the other side, and you have log w plus 2 log y1, sorry, that's really ugly. Okay, still pretty ugly. Okay, which is the same as plus 2 times the log of y1 squared, if you move that exponent up there, and that's equal to minus the integral of p of x dx. Okay. Now, this can be rewritten as the log of w times y1 squared. Okay. That gets us down to, and they put that in absolute values, which you really should be doing all along. Okay. That one you don't have to because it's squared. Okay. Now, I need more room. So I'm going back up right up here and write down what we've got so far. If you take an exponential of both sides of this, that gives you a w y1 squared is equal to e to the minus integral p of x dx. Okay, this is looking a lot like what we used to do. Now, one thing I neglected to do was do my plus c. We usually didn't when we did that p before, but we do need it now. So, what this turns out being, by a proper placing of it, you can put the c here. It's not the same c as we had there, but almost the same. Because you see, when you take e of c, that's a constant. And so let's just make that the new constant, c. Okay, before it would have been a c1 or something. They do that in the book. Okay, but anyway, now, to solve that for w, still need more room. So this becomes w is equal to c e to the minus integral p of x dx, okay, divided by y1 squared. Now we know what y1 is. Remember, that was the known function to begin with, okay? Known solution, okay? Now, we're going to use this next line right where it is, w is equal to u prime, okay, and integrate again. So I'm going to take out this line down here. That was true and useful at the time, but what we're going to do is write this as this will be du dw, I mean dx, du dx. Let me clean that up. That's ugly. Okay. Du dx, that's what w is equal to c e to the minus integral of p of x dx divided by y1 squared. Okay? And if you, again, write this in differential form and integrate both sides, I think I'm going to have to erase a bunch here now. Okay, so let's get all this out of the way. I hope I won't need it. I don't think I will. Okay. Integrate that again. I think I left a line that wasn't supposed to. This we don't need anymore. We've already dealt with that. Okay. Now we're where we need to be. Okay. This will give us u is equal to the integral of this thing. Now, I'm pulling out the c, they did too. The c here, integral of e to the minus the integral of p of x dx over y1 squared, okay? That's what we have there, plus c, some other c. And let's just make this a c1 and a c2 since we got two of them, okay? Now, they just randomly say we'll choose C1 to be 1 and C2 to be 0. And that then wipes out that. And that makes this 1. Okay? So there's what your U is. Okay? But remember U, there it is. Nope. Yeah. U is equal to that your y2, and this again, I would have put the y2 here in the first place. They have it, but they should. But now they stick it in again, so I don't know why they didn't have it there all along. That the y2, this new second variable y2, is now equal to the y1, and this may be y, okay? Y1 of x, because you multiply, okay, y1 of x, y2 is equal to y1 times u. Here is your u, so this is times the integral of e to the minus integral of p of x dx divided by y1 squared. Okay. And I think there was a c in, oh yeah, they chose the c to be 1. Okay. Now, that's how, in general, we get our second function. Now, this doesn't look easy. Usually it works out not badly. Usually this is a simple integral to do. That gives you an e up here. And then usually there's some technique you can use to integrate that. And if there is, then we're okay. I've left off my dx here, sorry. Because that dx carried on down to here. Okay. And there it was up there. That's why I'm missing it. Okay. Now, here I think we have a student coming in. Yes. Okay. Daniel's here. All right. While I'm waiting for the projector to come up, let me just make a couple of quickie announcements here. I think I've said this before. Okay, they published this final exam schedule, and to my best understanding, it's wrong, because they have the final starting on Monday, April the 29th, whereas both the academic calendar and the administrative calendar say Mondays. The final start on Tuesday, the 30th. Sorry. Okay. So we have class today, next week, and Monday, and that's it. Okay. Now on Monday, I'll give you your last test, which is the test from basically chapter 4. Okay. Now, I believe, yeah, you have turned in your research paper. You turned in test one, and I know you're still working on test 2, as long as you get that in. But I'm preaching to the choir here. I'm talking to the people who are not here. I need your research papers in. Now, 3 of you have turned them in, Dan being 1, but 3 people have still not turned in the research paper. 3 people have still not turned in test 1. Well, I may have gotten 1 since then. I think I've already graded it, though. And then test 2, I've only got 1 so far. Okay, so I need those in sooner rather than later. I'd rather not have everything come in on that Monday. Okay, but I'll take it. But as soon as you can get it, the better. Okay. The rest of the announcements, I think, I did want to ask this: are you graduating this term? Okay, good. So. The only thing with that, if you are graduating this term, and now talking to the people listening, hopefully you're listening, if you are graduating, you've got to have everything, you've got to have your final exam into me by Thursday of finals week, okay? I can't think what that day is. The first Thursday in May, which is the 2nd, Thursday, May 2nd, because your grades have to be in by noon on Friday. I've got to have your work in sometime on Thursday so I can get them graded and your grades calculated. Okay? So that's for people who are graduating. If you're not graduating, you have until the following Monday, which is the last day of finals, to get them into me. Your grades are due in by Wednesday. Okay? Noon. So I need those by Monday so I can get them graded Tuesday, average everything done, and grades in by Wednesday at noon. Okay. So that's all I know about there. Any questions on anything so far?
What day did you say I had to have my final turned in?
By Monday what day is that?
The 6th?
6th, Monday the 6th. Sooner is fine, but that's the last day. Well, that's when I need it by. I still have Tuesday, so if you can't get it to me Monday, Tuesday will be fine. But I've got to have grades in by noon on Wednesday, or else it's an incomplete. So, okay. Any other questions? Okay. Did you say you had one on
the test?
On the test? I'm not going to have time after class, so if you got it, might not be a bad idea to ask it now.
All I need is,
Because Wednesday, you know, this is Wednesday. I've got to go to the other campus as soon as this class is over. So.
I just need to verify that problem 7 is a Bernoulli's equation. If it's not, then I'm totally lost.
Actually, many of those you can use several forms. This is test 2, right?
Yes.
Number 7 on page 2.
Yes.
If I'm not mistaken, yeah, that should be. Well, I think you can use, I'm pretty sure you can use Bernoulli's. I believe you can probably even use separation of variables. So, but yeah, if Bernoulli's works for you, it should be fine.
Well, I tried it, and it looked like it was almost turned out to be a transient. That's where I was going to go.
Yeah. So, yeah, it should not be an issue. It's an initial value problem. However you solve it, you know, come up with a solution. But just glancing at it, it looks like that even would be separable. Yeah. So, but Bernoulli's probably will work too. Usually, if the sort of lower order thing works, the higher orders are sure to work. But that's not always the case. But sometimes if the lower orders don't work, you have to go to the higher ones, like Bernoulli's. So, yeah, so that should be fine. Okay. I haven't worked it that way, but it should be. All right. But, yeah, shouldn't be an issue there. Is that all you had?
Yes.
Yeah. Okay, good deal. All right, now, where we left off last time was top middle part of page 133, and what I've done since then is filled up almost 2 screens, so you can't see it all here, getting to the final answer. And basically the final answer, and they did some magic in there too, but their final answer was that y2, the second, okay, there was our original function, okay? It's a second order linear differential equation in y, and x is an independent variable. And we had gotten it down to the place where we had taken that out, and we actually had this form right here, okay? Which we then did that substitution. I think we introduced the substitution last time. We got it down to a linear form from a second order, second order to a first order form, which also happened to be linear and separable, separated the variables and fiddled around with them, did a variety of things, went back and plugged in what W was, which is U, du, dt, integrated again, and then substituted what U was, and U was basically this was what our U was, and went up here that y2 was U times y1, so we wrote the y1 in front, and this was our U. Ultimately, that we came up with this was U. They came up with some magical reason that C1 could be 1 and C2 could be 0. So that's why I put a 1 and a 0 to wipe that one out. Okay, this is usually something, hopefully, that you can integrate. And then once you've integrated that and plugged it in here, hopefully this is something you can integrate. And if it is, then multiply that by 1, and you get your second function. Because in second order, you need 2 linearly independent functions. This thing will make it linearly independent from that, by and large. If that comes up being a constant, yeah, you're down the wrong track, okay? But it usually will not. There's way too much in there for that to be a constant, as in your y1 is in the denominator squared, okay? It says it makes a good review of differentiation to verify that the function y2 defined in this equation here satisfies equation 3, which is that one at the very top, okay, and that y1 and y2 are linearly independent on any interval in which y1 is not 0, okay? Now, to do that, to do a first derivative of this and then a second derivative of this is really, it probably sounds very daunting, but it's not quite as bad as it seems. Remember that derivative of an integral is just what's inside, okay? So if you proceed to do that, I think you'll see that it isn't quite as bad as probably what it would seem like it is, but it's bad enough, okay? So I just as soon not have to show that. And then to show that it's linearly independent, like I said, just the fact that you have a y1 in the denominator of a radical, y1 squared, and on the outside, I don't see any way that could be linearly dependent. It would have to be. So we'll just leave that alone and go on to example 2, which is going to use this, okay? Now, I'll be referring back to this, but I've got to clear the screen in order to do example 2. Here's a function. This we're going to call our y1. This is equal to x squared. And they tell us that is a solution to this x squared y double prime minus 3x y prime plus 4y equals 0. Okay, now that's a linear second order ordinary differential equation. See if I can clean this x up a little bit there. That looks a lot better. Okay, some better anyway. Okay, let's first verify y1 prime is equal to 2x, y1 double prime is equal to 2. So this would be 2x squared minus 6x squared plus 4 times x squared. 4 times x squared, sure enough, is equal to 0, right? 2 plus 4 is 6, minus 6 is 0. Now we got that. Okay, hope you see. That's a pretty simple differentiation there. And 2 times x squared, that's where that came from, minus 3x times 2x is minus 6x squared, and plus 4y, y is x squared, that's plus 4x squared. Yep, that's equal to 0. Okay. So we see that is a solution. Okay. So I'm going to erase this. We know, we verified that is a solution to that differential equation. All right. Done. All right. Find the general solution of the differential equation on the interval from 0 to infinity. All right. I see no reason to limit. Now, I have a feeling what we're going to do is going to make it obvious why you have to say 0 to infinity. And the first step will tell us that. Well, to get it into our standard form for doing this, remember we want the leading coefficient to be 1. Remember? Top of the page, y double prime plus p of x, y prime plus q of x, y equals 0. So we need to divide everything on both sides by x squared. Okay? Of course, the right-hand side is still going to be 0. So now we have y double prime minus, okay, time out. Number 1, now we see why x can't be 0. Well, of course x couldn't be 0, because if x is 0, we have 0 equals 0 in trivial form. So, obviously x wasn't able to equal 0 at the beginning. Now it's really obvious why it can't be, because we're just divided by x squared. If x was 0, that was a totally illegal move. Okay, but it couldn't have been 0 anyway. So it couldn't be from minus infinity to infinity, because it can't be 0. So why not take it all positive values? not counting 0, and on the thing here, it says on the interval 0 to infinity. And since, okay, we'd like it to be continuous, so since it can't include 0, let's just start at 0 and go to positive infinity. You'll see there's another reason. It's coming up in a minute, right soon. For instance, this is going to be minus 3 over x y prime, right? Plus 4y over x squared equals 0. All right. Now, thinking back to what we just did, one of the first things we do is integrate the p of x dx, okay? And we want yeah, let's do just the p of x. I was trying to decide whether to include the minus sign or not. Let's not. So let's do our, well, in the form the p of x should be. So we'll include the minus sign. The p of x here is minus 3 over x. Okay? And we're going to integrate that dx. Okay? So the integral of that would be minus 3 times log x. Okay? All right. Minus 3 times log x. Okay? But in our form, this is where I was struggling with it a little bit, it's e to the minus the integral of that. So then we do the e to the 3 log x, which is the same as e to the log x cubed. Okay? Well, e to the log x cubed is just merely x cubed. Because the e undoes the log, log undoes the e. Okay, not?
Oh, that's right. The whole log thing, the moving the base and the, that's
yeah.
right.
Yeah, if you have something multiplied by a log, you can move that up and make it the exponent in top. Okay, that's one of the rules of logarithms. And the reason we did that is so we could then make that x cubed.
Now, what happened to the negative?
Okay, that's the thing. In our form, okay, this is a, okay, the minus got down there, right? And then if you look at the form, and I wish I could go back a slide, but I can't. If you look at what we have here, y2, what we did last time, is equal to y1, that's a function of x, and so it's y2. Why they left it off, I don't know. It's the integral of e to the minus integral of p of x dx, okay, over y1 squared. So this was the integral. I was really toying with the idea here how to deal with all these minus signs, but sure enough, the first one was assuming this is a plus here, so we had to include that as our p, but then you take the minus integral of that, which would be minus a minus, which is plus. So that's where it went, because you put a minus in front of that. Okay? And like I tell even my Cal 1 classes, these minus signs are just there to trip you up, okay? And they do a great job of it, because you have minus a minus a minus a minus, you know, and it just is hard to keep up with which one is negated what and how many times and stuff like that. So that is the form, but our p of x turned out being minus, and when you did minus the integral of p of x, that made it plus again. Okay, so that's your numerator here. Okay, now if you take that, that's your numerator, e to the that, okay, and then divide that by y1, but y1 was x squared, Okay? So now we have the second integral is y1 x times the integral of x dx. Okay? Yo! Okay? I think I left off a dx here. Yeah, there were two dx's there. Okay? Well, the integral of x dx is x squared over 2. Okay? And that's multiplied by your y1, where your y1 was x squared, so your y1 is equal to x squared, and y2 is equal to 1/2 x to the 4th, because it's y1 times that. No. Oh, no. Yeah, I messed it up. Sorry. Back up. I thought that was coming out rather strangely. Okay. Sorry. I forgot to square the y2. Oh, y1. Okay. Because that didn't look like it was very... Okay. So y2 is equal to y1 of x. I'm not going to fill that in yet. This, remember, I just put it over x squared. It was x squared squared. So this should be over x to the 4th. You see? Your y1 was x squared, and here you're divided by y1 squared, which is x squared squared. So that was your x cubed, which was this thing, divided by x squared. That gives you x to the 4th. So this integral is now the integral of dx over x. Okay? All right. Now, that integral, that now becomes y2 is equal to y1 of x. Let's go on and write it out as x squared times log x. Okay. Now, notice they aren't putting any more plus c's or anything else in it. I can't rationalize that for sure, except up there above when we're doing the thing, well, let's just arbitrarily choose this one to be 1 and that one to be 0. So they're letting them be anything they want to, so we're just assuming they're 1 always. So that's the only way I can rationalize that. So what is your general solution? That's what I asked for. I found the general solution. The general solution y is going to be some c1. There is your constant, okay, because it's a second order linear differential equation. You have a c1 times your y1, which we know to be x squared, plus c2 y2, which we now have determined to be x squared log x. So your y is equal to c1 x squared plus c2 x squared log x. Okay. There's your general solution. c1 x squared plus c2 x squared log x. Okay. Don't need any other plus c's or anything else, because those are your constants. Those are your the arbitrary constants that you use when you're doing your, what do they call that procedure? Superposition. Okay. So there is the example, the one and only example, well, second example in 4.2, and that was 4.2, okay? I've already assigned most of these before. Any of the odds 1 through 15 that are in the back of the book, any of the odds 17 through 9, either 17 or 19 if they're in the back of the book, 21 if it's in the back of the book. Usually the discussion problems are not in the back. So that was it for 4.2. Shortest section, I think, in the text, okay, that we've hit so far. So let's move on to 4.3. Okay. Now, it almost feels like we're backing up, and we kind of are, but we needed the general form for the more complicated case. Now we're going to back up and do some simpler things using the similar case. We're going to return to first-order differential equations, really backing up, more specifically, homogeneous or homogeneous linear equation of the form ay prime plus by equals 0. Whoa here. Now that is pretty simple. I don't know why my pen's not writing completely. Okay? Where the coefficients a, of course, cannot be 0, but can be any other constant, and b can be any constant. Okay? All right. Now, this type of equation can be solved either by separation of variables, pretty easy to do that way, or with the aid of integrating factor as in a linear solution. But there's another solution method, one that uses only algebra. Okay? Now, before illustrating this, we'll make one observation. If you go to solve this for y prime, then you can rewrite that as ay prime is equal to minus by, right? Just subtracting by from both sides. Dividing both sides by a, and then saying y prime is equal to sum. Who cares what b and a are and what signs they are, anything else? Just make it k times y. Okay? Where k is a constant. May be positive, negative, it doesn't matter, depends on the signs of a's and b's, but it's some constant. Okay? Now, this observation reveals the nature of the unknown solution y. Remember, they always said, well, here's a solution y. Okay? Well, about the only thing we can say that is always going to work with that is if y is equal to some form of an exponential function. So let's let y equal e to the some arbitrary mx. Okay? All right? Now, then y prime is equal to m e to the mx. Agreed? Okay? So then we have m e to, goodness gracious, I can't write. M e to the mx is equal to k e to the mx. Because here's your y is equal to that. Y prime would be e to the mx, chain rule it times m. And then when you plug that in, m e to the mx is your y prime equal k times y, which is e to the mx. So this will be true anytime m is equal to k, right? Okay, they're doing, strange. and they kind of get me lost here. I know what they're heading for, but their way of doing it is just so bizarre. They go back to this form, but using this solution that we just did here. Okay? Again, let y equal e to the mx. And then y prime is m that. So then if you go up to this equation, you have a m e to the mx is equal to oh yeah. See, here we divided by a. We're not going to do that now. So let's go back to our b. So this will be, I believe it's a minus. No, in this form, not equal to, plus b e to the mx is equal to 0. It'll come back, I think. Okay. Now, since you have a e to the mx in both terms, you can factor that out. You have a am plus b is equal to 0, right? Now, e to the mx is never equal to 0, ever. Your exponential function either goes like this, if m is positive, it goes like this if m is negative, but it never reaches 0. Gets close, but never reaches 0. So that is never 0. So you can divide it out. Well, now you have a new equation that am plus b has to equal 0. So m is equal to minus b over a, which is the same thing we got here. I don't know why they went around their elbow to get to the ear, but they did. And so if y is equal to e to the mx is a solution, then you and let's see, m is minus b over a, you can come up with any other, well, hold off on that for a moment. Yeah, that is your solution. Okay. Now, now they jump to somewhere else. To illustrate, consider now I'm going to erase most of this, all of this, because it's going to be pretty easy to do. Let's say this is a differential equation. 2y prime plus 5y is equal to 0. Again, we're only considering the homogeneous case where it's equal to 0. Later we'll come back and do the other, okay? Non-homogeneous or non-homogeneous, okay? Now, you could say let y equal e to the mx and then carry on through, but basically you know what it's going to come out be. It's going to come out that 2m plus 5 is equal to 0. We just did it before with a's and b's. That's what it came out being, right? Okay, 2a plus b equals, am plus b is equal to 0. Here your a was 2, your b was 5, so it's 2m plus 5 is equal to 0. Okay? So now we know that m is equal to minus 5/3. That's your minus b over a, by the way. Okay? But you don't have to remember that. Okay? So we know that y is equal to e to the minus 5/3 x is a solution. Okay? So we can just put an arbitrary constant in front of it, C1 or just C, and there's your solution to that linear differential equation. Huh? It's a 2, not a 3. I don't know where the 3 came from. I just looked at that myself and say, where is that coming from? Okay. Okay. So, m is equal to minus 5/2, so there's your solution. Okay. And you can go back and plug it in, okay, y prime is going to be minus 5 halves, e to the minus 5 halves x. So that would be 2 times 5 halves, so it's minus 5 times 10 to the minus 5 halves x, plus 5 times, C1's there, but 2, e to the minus 5 halves x, and that adds to 0. So no, that works. Okay. Now, and that's a general solution on the interval from minus infinity to infinity. Okay? In this section, we'll see that the foregoing procedure can produce exponential solutions for homogeneous, linear, higher-order differential equations as long as the coefficients are all constants. Okay? Real constants. No imaginary constants, no functions of x, real constants. Pretty simple case. Yeah. So, now they're going to start giving names to some things here. So let's start with, and frankly, hopefully this seems pretty easy, because it is pretty easy stuff. Let's say we have this. Go back to letters again. AY double prime plus BY prime plus C is equal, CY is equal to 0. We're doing homogeneous or homogeneous forms. Okay? If you did, let y equal e to the mx. Okay? Then y prime is equal to m e to the mx, and y double prime was equal to m squared e to the mx. Right? Plug them in. A times m squared e to the mx plus b times m e to the mx plus c e to the mx is equal to 0. Oh, my nose itches. We're going to have company. Okay. Again, you can factor out e to the mx, and you have am squared plus bm plus c is equal to 0. And because e to the mx can never be 0, you can divide it or throw it out. That factor can't be 0. That means this factor has to be 0. That's a standard quadratic, right?
Yeah, that's quadratic.
Just a quadratic equation. That's why they say this is doing it by algebraic method. Your m is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Or if it happened to be letters, you could factor it, okay? But those are going to be your two solutions, okay? But that's going to be the equation. Now this is given a special name. That is called, this equation right here is called your auxiliary equation. Your auxiliary equation. Okay, and like I just said, one of your m1 is going to be minus b plus the square root of b squared minus 4ac divided by 2a, and the m2, the second one, is going to be minus b minus the square root of b squared minus 4ac over 2a. Now, problems arise when this thing is equal to 0. If that's equal to 0, then we're going to have to do something like we just did with our power reducing things that we just did, come up with the second one some other way. So we'll get to that later. Another problem would arise if this thing comes up being complex. In other words, i's in there. This is greater than that, so it turns out being negative under the square root, then you have i's. But we're going to come up with a method for solving that as well. In fact, it's a pretty straightforward method. Amazingly straightforward method. Now that could come up being an irrational number. It's awkward, but it's doable. Okay. And if it comes out being an integer, in other words, if that thing, the discriminant thing under the radical is a perfect square, you're fine. You just come up with two rational numbers. And a lot of times it will be, but if that was the case, then you could have factored that in the first place and you wouldn't mess with all auxiliary equation, I mean with the quadratic formula. Okay? So, there will be three forms for the general solution. Okay? In other words, is this discriminant? I don't know if you remember back in some type of algebra class, you called that the discriminant. If that thing was positive, then you get two distinctly different M1s. Maybe irrational, may not be, whatever, but they are formed. So you get two real and distinct numbers. If this thing, though, is 0, you only get 1, and then you have to come up with a different y2, okay, because you only have a y1 there. But if these come up negative, if this thing comes up negative, then you have a complex conjugate, and you have to deal with those. And we'll show how to do that just momentarily, if we've got time. How much time do we have? Huh?
5 minutes.
Is that all? Yeah. Good. Yeah. Okay. So let's the first case where that is positive. You have two distinct real roots. Okay? We've already shown what that is. That would be y is equal to C1 e to the whatever that real root is. Do they write it all out? No, if they just leave it m1x plus c2 c2 e to the m2x. I left off my e here. That's it. You just write it down. Now, if those are, irrational expressions, they're awkward, but they're just there. They're doable. Okay? Perfectly fine. So that's your two solutions, and that's what it is. There's nothing bad about it. You just either factor this thing here if it's factorable, or use the quadratic formula if it's not, and use those two as the roots. Okay. Now, case 2 would be a repeated. In other words, this thing is 0, so you only have one solution. Okay? And if you use that way we just did, they give a little bit of explanation for it, but this is when M1, M2, okay. Discriminant is positive, okay, greater than 0, M1, M2 distinct roots. Okay, done. When discriminant, yuck, it's going to flick off, but it'll come back. When the discriminant is equal to 0, you only get one repeated root. So then you have y is equal to C1 e to the mx. That one and only one root, right? But then you do this, and it's really simple, and it seems hard to believe, plus C2 x e to the mx. Now, where did that come from? Go back to what we just did, and you're integrating the p of x, all that kind of mess, and you wind up being the y1 times the integral of dx, which is just x. Okay? So there is your second. First, you get two m's. They're usually conjugates of each other, or they're just two completely separate numbers. Just plug them in. Those are your two roots. Okay? However, if you get only one root, discriminate equals 0, basically it's minus b over 2a. You've seen many times before. Then that's your first one. And the next one, just multiply x by that e to the mx. Those are linearly independent, and that's what you get. Pretty nice. However, the third case, when you wind up with complex roots, and that's where we may have time. I kind of doubt it, but let's get started. So I'm going to go from a new screen here. because this is going to take a little bit. Okay, let me know when it's time, because I don't want to go over. I've got to leave too. So M1 and M2 are complex. So your discriminant, b squared minus 4ac, is less than 0, which means you got imaginary roots here. In other words, the way to say this is 4ac is greater than b squared. If that's the case, this thing's going to turn out negative. When you have negative, you wind up with complex roots. So your M1 would be some alpha plus I beta, or beta I. Many other books say beta I. This book says I beta. Your M2, because it's a complex conjugate of it, is the same alpha minus I beta, or beta I, whichever you want to call it. Where beta is whatever okay, remember your b over 2a minus b over 2a, that's your alpha. And your beta is the square root of b squared minus 4ac, which happens to be an imaginary number. Okay, I mean, a negative number, so you have to do an I in there, and the I is the basically square root of 4ac minus b squared, the reverse of that, over 2a, and that, then you pull an I out of it. So that's where that comes from. Okay. Don't sweat that too much yet. Things amazingly make a lot more sense in a minute. Okay? So what your solution then is y is equal to, because there's your M1 and M2, just like before, C1 e to the, but this time you do alpha plus I beta x. There's your M1 plus C2 e to the alpha minus I beta x. There's your M1 and M2, just like they were in case 1, because you have 2, but now they're complex. Now here comes the magic. And this is really pretty incredible magic. Good old Leonard Euler, ancient mathematician, incredibly brilliant character, came up with this formula. And this is absolutely true for anything. E to the I theta is equal to cosine theta plus I sine theta. And you might say, so? I mean, what in the world is that talking about? Well, here you have an I beta x here. I don't think I'm going to have time to carry it through. So that's where we'll pick up next time. We've introduced Euler's formula, and we'll plug that in this form that we have here and see what comes out. And it's really amazing what comes out. It's just really phenomenal. And yeah. Nope. I managed, no, there it is. Nope. Have I managed to lose my eraser? Can't believe this. I seem to have done so. But let me see if I can. Ah, there it is. There it is. Okay. So we'll pick up there next time. Now, did we get enough to do any homework exercises in this section? I don't know. Try start working on any of the odds 1 through 13. If you come up with any of those that come up being imaginary, stop. We'll do those later.
I'm not sure I remember how to get imaginary.
Okay.
Imaginary is just
if your square root is negative, that b squared minus 4ac, that's under the square root. If that comes up being a negative number, then you pull out the minus 1 and make it an I,
That's right.
and then what's ever left over,
Okay.
that becomes your, what they're calling the beta. Okay. So we'll go from there, and we'll do some that does come up, and it's really amazing how simple that gets, in a sense. It's not simple to get there, but once you're there, it's simple from then on, relatively speaking.
Yeah.